My goal here is to help you understand how to write maintainable code. I won't be concerned with how easy code is to initially write. The reason for this is that code is only initially written once, but has to be continually maintained. I'll be focusing on what I think is the most important aspect of maintainable code, separating what you control from what you do not control. Now, disciplined practice of test-driven design will be a great help in writing maintainable code. However, to illustrate the difference, I'm going to use an example that was not test-driven. So let's have a look at this sample application in Scala. Here I extend app, which is Scala's way of designating that this is an entry point. I further clarify this by just naming the object entry point. Next, I grab the current time from the system clock and assign that over to start time. Then I grab the path from the first command line argument, read all bytes from that path, and then convert those bytes into a string using character encoding UTF-8 and assign that to target. Next, I say hello to that target and emit that to the console. Then I check the time again and use that time to compare to the start time to compute the duration that the whole process took. Finally, I emit that duration to the console in milliseconds as well. So we want to make this code easier to maintain. So why is it hard to maintain? Well, imagine if someone changed this so it did something different. How would you know? You wouldn't know because it's not under test coverage. So why isn't it under test coverage? Well, think about what it would take to write a test for this. The clock's going to be different every time to run the test. Also, it emits lines to the console, so how are you going to capture that in a test? So it's not under test coverage because it's hard to test. So how do we make it easy to test? Well, that's where we separate the things we don't control from the things we do control. So by things we do control, I'll start referring to that as the deterministic parts of the app. These are the parts of the app that are defined entirely by the rules of the programming language and only use libraries or functions that are also entirely controlled by the rules of the programming language. The non-deterministic parts are parts that are not defined by the programming language because they come from the operating system. So let's take a look at what types of non-determinism we have here. Well, first we have a system clock. The rules of the programming language don't define what this says. This is given to us by the operating system. All the rules of the programming language do is delegate to the operating system to ask what it says. Next up we have files. That's also controlled by the operating system and not the rules of the programming language. Finally, we have emitting a line to the console. So again, not defined by the rules of the programming language, the operating system takes care of that for us. Now, so that's three types of non-determinism. There's a fourth one that's a little more subtle. That's this arguments right here. These are actually injected to us from the operating system. So it's a little unique because these three types of non-determinism, the clock, the files, and the console, these are cases where we are invoking the operating system. This arguments, we got that because the operating system invoked us. Now it's time to start actually separating the parts we do control from the parts we don't control. So looking at this line 9 here, we see that we actually have a mix of things we don't control and do control on the same line. We don't control the file system, but we do control the string, constructing the string once we have the bytes. So let's go ahead and just split everything up. So I'm going to start with the clock up here. Okay. Next up, I'm going to grab the path name. And then do the path. That's fine. Next up we get the bytes. And that string construction is fine. Okay, and then let's also get that from the same clock. And here we started this start time, so let's go ahead and call this end time. And for our purposes, we don't need these things to be private, so let's get rid of those as well. So now I've separated everything onto separate lines. So you might think this is a little more complicated because, oh, look at all these extra lines, but I've made it simpler in at least one way by allowing me to give names to all these parts. So sometimes this can be overkill, like you could argue that in this case, in some of the cases here, but I find it's better to err on the side of splitting things up too much rather than leaving too many things together, because I find it's easier to merge things back together if it was a mistake than it is to split them apart. Now that we've got everything split out, it's time to start isolating our four types of non-determinism. I like to start with the entry point nondeterminism because I find that's usually the most harmful. It's never a surprise to me when I see a bunch of application behavior in an entry point that that application behavior is the one thing not under test coverage. So let's just take care of that right away. That's extends. Okay. I'm just going to grab the whole block. And put it down here. And now I've figured out what the entry point was in fact doing. It was forwarding along the command line's arguments, and that's the only thing it should have been doing. So for now, let's go ahead and constructor inject that. And up here in the entry point, we'll just create an instance of the application behavior. And run it. So now we've separated out entry point concerns, which is forwarding along the command line arguments and invoking the application behavior, from the concerns of the application behavior. And as you can see, the application behavior is now easier to test because we've separated out into this class where our test can just pass in any old command line arguments it wants. Next, let's take care of the system clock. I'm going to remove that concern from here. Now that tells me I need to constructor inject it. And then the compiler tells me that it needs to be up here. So go ahead and pass it in. And there, now I've made the clock testable. Now this clock here is behind an abstract class. In order to test it, you just have to create a fake stub or mock of that abstract class. It only has 3 methods. In this case, the only one you're actually going to have to implement is the instant method because that's the only one we need. So here we've made the clock easier to test. But if you look up at the entry point, we didn't do as well. Now the entry point has more concerns. It's not just concerned with forwarding along the command line arguments and running the application. It also has dependency injection concerns. So let's go ahead and take care of that right now. I'll go ahead and duplicate everything, and then we'll remove what is not appropriate for each place. So here we have a clock. We're going to need the application behavior. And we will not be responsible for running it. And we will have to be provided the command line arguments. And forward them along to the application behavior. So now let's look at what we need up here. In our dependency injection, we're going to have to give it the command line arguments. We don't need to worry about the clock. And we do have to invoke the proper entry point. And there we go. So now I've separated dependency injection from the entry point. So notice about the entry point here, no matter how complicated my application gets in the future, this never has to change. So you can see all it does is forwarding along the command line arguments and choosing what the entry point for the application behavior is. Everything else, so if you look at dependency injection, no matter how many collaborators we have, no matter how many new classes we have, no matter how much behavior there is, no matter how much dependency injection there is, this portion right here never has to change. Next up is the file system. And here it is. So let's go ahead and get that from somewhere else. And what I'm practicing here is a way of doing top-down design. I make the change first that will force me to make all the other changes, and it'll let the compiler help me figure out what else I need. So this is telling me, the compiler here is telling me that I need files. So let's constructor inject that. This is getting too long, so let's put that on a different line. And I'm going to put files behind a contract. Just call it contract for now. And which means I'll have to define that. And that needs to read all bytes. Okay, so now we have a contract for the file system, and again, top-down design, which has helped with the fact that this language is statically typed, tells me exactly where my problem is. So let's go ahead and put the actual files here. And now I know I need to define it. And we'll just go ahead and use the real one, which means I have to implement that. Go ahead and extend the files contract. And there we go, and then I will just pass straight through to the read all bytes. So notice I have no logic here, I'm just a straight pass through. Object here is just Scala's way of saying it's a singleton. Class has instances, and traits are analogous to a Java interface. So now, files is easy to test. Now, you could argue that this here needs an integration test, but since there's no logic, and it's just passing right through, there's really not much value in providing an integration test for this, because all you're really checking to see is that Java implemented their files correctly. And if that wasn't working, the Java community would have noticed by now. What you really need to test is anything that can possibly break. And this is really hard to accidentally break because it's just passing straight to the file system. There's no logic in here. So, and even if you needed to add more methods to the files from operating system, you would just add new methods. You wouldn't change this one. So again, not much use of testing it. Now for dependency injection, I don't like relying on type inference. So here I like to actually specify the types. And the reason for this, as you'll see in a moment, this is files contract, is because I don't want to accidentally have this application behavior depend on the implementation details of the files from operating system, for example. So by specifying the type right here, I can guarantee just in the dependency injection portion that this files that is passed in at compile time does not have access to anything in the files from operating system. If, for example, the application behavior was accidentally depending on something from this implementation, the compiler would catch it. So let's also handle that here. Now, I don't have a problem with type inference in general. It's just for dependency injection, I don't like to use it. Everywhere else, I think it's just perfectly fine, and it a lot of times makes the code a lot simpler. Just, I don't like it in the dependency injection. Next up, let's take care of the output to the system console. So here it is. And instead of these printlns, I'm just going to emit. And up here, emit. So again, I'm using top-down design. I'm letting the compiler force me to do what I need to do. So it takes a string, returns a unit. A unit is just Scala's version of saying it returns nothing. So that tells me I need some way of emitting it here. And now this line is getting too long, so let's just split that up. Okay, So now the compiler tells me I need an emit function. And again, not relying on type inference, I like to specify the type. So string goes to unit equals, we'll just assign it to println. So this line right here is saying the identifier emit has type of a function that goes from a string to unit, and I'm assigning it to println. So now let's check on how easy our application is to test now that we've broken it out like this. Keep in mind we only need to test everything that can possibly break. So first off, we have the entry point. So the entry point never has a reason to change. And all it does is it forwards along the command line arguments and initiates the application behavior. So never has a reason to change. If you've ever seen this work once, you can be pretty confident it's always going to work. The only way this could foul up is, let's say the operating system didn't forward along the command line arguments properly. Well, if that's the case, you have a problem that's outside of the scope of your application, so a test isn't going to help with that. So this really doesn't need to be under test coverage because it's not part of the code that could possibly break. Next up, we have dependency injection. This is really tested by the compiler. So for example, let's say what types of mistakes could I make? I could accidentally put the clock, put some parameters in the wrong order. But again, notice I get instant feedback. So compiler's helping me there. I don't need to test that. What else could I do? I could forget to define something. Again, compiler gives me instant feedback. So this doesn't need to be tested with a unit test because the compiler is really providing me all the testing I could possibly need. What else? I could forget to put in the command line arguments. Again, I get an instant feedback right there. So next up we have the files contract. No code here, it's just an interface, and yeah, nothing to test there. Next up we have files from operating system. So here you could argue you could need an integration test for this, but we have no logic in here. All we're doing is passing straight through to the file system. So if this was broken, chances are the Java community would have already known about this. So there's not really much value in testing this since it's just passing straight through to the Java library. Now there are some cases where something like this could be worth testing. For example, if this were a class that were accessing a database and that's called a stored procedure, and that stored procedure had conditional logic, let's say two sides of an if statement, well then you would need an integration test, one for each side of the if statement, or two integration tests I should say, one for the if, one for the else. But in this case, since we're just passing straight through and there's no conditional logic, there's really no point in testing this. You're not getting any value of it. And could it possibly break? I suppose, but again, how likely is it that the files library is going to break and the Java community doesn't notice it? And I don't think that's really something worth worrying about. So finally, we get to the last class, the application behavior, and here's where we see the real benefits of how we structure our code in order to make it testable. So our test can new up an application behavior. It can pass in any old command line arguments it wants. We've got the clock here, which is an abstract class, so our test can fake, stub, mock the clock. So in this example, how might we test it? We would probably pass in a list of values that the clock, or at least our stub clock, would be, its constructor would have a list of values, and it would just return those values in order, so it would have a variable to indicate the index of which value it was pointing to. So you pass in two values. The first time it returns the first value and then increments the pointer to the next value, and then it returns the next value, and then you're done. So you can pass in any 2 points in time and test how it works. Next up we have the files contract. So what might the fake stub mock look like for this? So this would probably be a stub, and it has read all bytes, so it would probably be implemented by a hash map that, given a path, maps to an array of bytes. And that's how the stub could work, so that way you can emulate any set of bytes you wanted, and maybe even provide some further utility functions. Maybe you map it to a string internally, and then just write logic inside the stub that actually converts it to the bytes. So that's another way to do that. Finally, we have this emit, which goes to capture stuff that goes to the console in the production app, but in the test, you would probably pass in a function that appended to an array buffer. That way in your test you could check to see, was the array buffer of size 2? Did I omit this line? Did I omit this line? So did I omit 2 lines? And then you could check the array buffer. You could say, hey, what's your first line? What's your second line? And see if they exactly match your expectations. So the subject is how we make maintainable code. So how does structuring code like this make it easier to maintain? Well, one of the things it does is it makes it very easy to write unit tests. The way we've put everything we don't control behind an interface, it makes it very easy to write unit tests. And when it's easier to write unit tests, you tend to write a lot of them. And really, 99% of your code should be under unit test. In fact, all the logic of your code should be under unit test. And the nice thing about unit tests is they are lightning fast. They don't have to talk to the file system. They don't have to talk to anything slow. So when you have a lot of tests when the tests are all fast, it's a lot easier to run them all the time. So you got a lot more tests run all the time. All your logic is under test coverage. It gives people the confidence that they can go change code without having to worry about breaking something as much. So say, for example, someone wants to make a code change. They say, oh, this is the area of the code I need to understand. So they understand that, they write their tests, and they change that code. And if they needed to understand a different part of the code, well, chances are the other unit tests are going to catch that. So then they'll realize, oh, these other unit tests caught the code so now I need to go understand that code too. And then they go understand that, decide if the code needs to be changed or the unit tests need to be changed, and they move on. So this really makes you able to code a lot faster, because if contrast that with code that's not under good test coverage, people tend to be afraid of changing code because they're afraid of breaking something, and they don't have confidence in their ability to know that they did break something. So that makes people a lot more timid, which in turn makes you a lot slower in changing code. So, and it allows you to change things without having to understand the entire app. You can focus on understanding just the parts that are relevant to you. So the big takeaway here is make sure that to make code maintainable, you want to separate the things you control from the things you don't control. And the way we've done that here is we've just taken everything we don't control and we've put it behind a contract. So just remember that most important thing to understand with writing maintainable code is separate your determinism from your non-determinism.